on my screen, or right on top, you will see sections 4.5 and 4.6 will not be examined because it involves approximation. Okay, so when you have binomial and you have Poisson, you can use the normal distribution to find probabilities. But anyway, it's very similar to what we've done before, binomial and Poisson. Okay, you can find probabilities of one using the other. So that's why we decided to skip 4.5 and 4.6, and we go straight into 4.7. So here we're going to be looking at the sampling distribution of the sample mean. And you will see here, guys, you see the word sample, and then you will see the word mean, okay? So that's why we refer to the distribution of the mean as the sampling distribution, because it involves samples. Now, the mean is an example of a statistic, okay? The mean is an example of a statistic, as well as the variance. Okay, we will not have a look at proportion, but because we can also infer on proportion. Okay, so here, as I said previously, we have a population, and from that population we draw a sample, and from that sample we can calculate many other values. These values in our course is referred to as the statistic or a statistic. Okay. Again, hence you will hear the word sampling distribution, because I will demonstrate just now that the mean differs from sample to sample. So when it differs from sample to sample, it has its own distribution, and that distribution is referred to as sampling distribution. And for the last point here, we will have a look at the last point when we do chapter 5. Okay, chapter 5, in fact, is the most important in stats. All right. So again, when we reach there, you will see what we mean by sampling distributions of other parameters. Okay, so here, as I said, in this course, we will only look at the sample mean, okay? The mean, X bar. So again, X bar is referred to as a statistic, and it varies. So when it varies, we refer to that distribution as the sampling distribution. Now, as an example, okay, guys, this is for example, not from example, okay? So it's an example. All right, suppose we have a population of size 4, okay? The values are 2, 4, 6, and 8. And this defines the sample space S, okay? And guys, do not confuse the sample space with samples, okay? The sample space contains all possibilities, all right? As we've seen in one of the chapters, chapter 2. Okay, so that's the population that makes up the sample space, and here they are the values 2, 4, 6, and 8, okay? So for this example, we're gonna be drawing two values and make one pair of values. So we pick a value from here and place it back into the space, into the set, and then draw another value. Okay, so that we have a sample of size 2. Okay, what we mean by this is the following. Okay, we have 4 values, S, okay, 2, 4, 6, and 8. And here, suppose I draw. On the first draw, I get a 2. I put it back. And on the second draw, I may again get a 2. So that constitutes my first sample, the pair of values, 2 and 2. Okay, or it can happen that I draw a 2 on the first draw, put it back, and on the second draw I get a 4. So here this is a sample of size 2, here as well. Okay, and for the sample mean for the first sample, then let's denote it by x1 bar. So 2 plus 2 divided by 2, that's 2. And for the x2 bar for the second sample, 2 and 4 is 6, divided by 2 is 3. So you can see here, with values from the population, we have different sample means, okay? But the sample size is still the same, okay? So if you do this, you will see a pattern. So you can have 2, 2, 2, 4, 2, 6, and so on. And we have 16 possibilities. Guys, can you see my screen?
Yes.
Guys, can you see my screen?
Yes, sir.
Because someone can't see my screen. Can you? Yes, can you see my screen?
No, I can.
Yeah, I can.
Okay, guys, Shlangeni, just try to adjust your computer. Maybe your screen is not adjusted properly, because the other guys can see. Okay?
Okay.
All right? Shlangeni?
Yes.
Is that okay? Okay, cool. All right, guys, so here we have the sample sizes are the same for all the samples, okay? And we have 16 possibilities, okay? And the last one is 8, 8. We can draw 8, put it back, and this, on the second draw, you obtain an 8 again. So the mean for the last sample of size 2 is 8, 8, 16 divided by 2 is 8. So you will see the X bars differ, okay? I have only one value of 2, 2 values of 3, 3 values of 4, and so on. Okay, so the sample means distribute differently. Okay, so again, I will show you again what I mean by this. Just bear this in mind. Okay, so for different samples but of the same size, we can obtain different sample means. Hence the word sampling distribution. They distribute differently. Okay, so all right, guys. So here xi. Okay, so xi bar takes on different values. For our example, it runs from 2 to 8. Okay, so because they can take different values. X bar will have its own mean and its own variance. Okay, which means that X bar then becomes a random variable because it can take on different values. So X bar is a random variable. Okay, bear this in mind again. All right, so in any case, a statistic is a random variable. Okay, so hence, again, as I said, we talk about the sampling distribution, which I will demonstrate just now. Okay, for our example, again, guys, because we have different values for little x bar, which means that big x bar is a random variable taking on values little x bar, okay? Implying that x bar, the big x bar here, is a random variable, having its own mean and its own variance. So for our example, as I said, there were x bar appeared once only, okay? So we have only one value of x1 bar. And 2 values, x2 bar appears twice, okay? There's a counts 2, okay? So 3 and 3. For x3 bar, we have a count of 3, okay? The value here is 4 once, the value here is 4 twice, and the value here is 4 3 times, okay? So x bar taking on value 4 appears 3 times, okay? So there's a count of 3. So the frequency for 5, if you look up at this table, you will see there will be 4 5s, okay? So there will be 4 5s. 1, 2, 3, and 4, okay? So that's the distribution for the different values of x bar. Okay, so how do we check if this is correct? The total count has to be 16, okay? Because we have 16 possibilities. So here the total count is 16, and what's the PMF, okay? The probability that x bar take on little value x bar, little x bar. Okay. So here from chapter 3, okay. So here it appears once out of 16, okay. So the prob that x bar equals to 2 is equal to 1 over 16, and the prob that big x bar equals to 3 is 2 out of 16, and so on. And again, as a verification, you can add all these PMFs, you will get 1. Okay. So this is what is meant by the sampling distribution of x bar, of the sample mean. It differs, okay? So it distributes itself accordingly, according to the values that you see in this example. Okay, so because it is a random variable, it has its own mean, and to find the mean of x bar here, big x bar, we use the same formula from chapter 3, but with a bar on top, okay? Sum x bar, PMF x bar, okay? So we multiply each, okay, and then add. So that is 2 by 1 over 16, plus 3 by 2 over 16, 4 by 3 over 16, and so on. I have verified it. The value is 5. So here the expected value of the sample mean is 5. That is the mean of the means. Okay, the mean of the means is 5. All right, and we can also find the variance of x bar using the formula again that we have seen previously. We do the sum first and then subtract ex bar to the square that we have just seen. Okay, 25. So here, guys, simply square each x bar. So here's going to be 4 by 1 over 16 plus 9 by 2 over 16, and so on. And then do this difference, you will get 5 over 2. Now, guys, bear these two values in mind. Okay, E of x bar is 5, and variance of x bar is 5 over 2. Okay, so now let's denote what we have seen previously, the 4 values that we started with. Let's denote that set by x, okay? The random variable x, all right? Consisting of the set 2, 4, 6, and 8. Now, from here, how do we find the population mean, eh? The population mean, all right? Because for this example, these are the population values, consisting of 4 values, 2, 4, 6, and 8. So the pop mean will be, how do we find this mean? Is by adding the 4 values divided by 4. Okay, so here you will arrive at 5. So please verify these guys. And here as well, the variance of x from here is also 5. Okay. All right. So what's the PMF, or what's the probability of obtaining a 2? 1/4, isn't it? And the prob of obtaining a value of 4, 1/4. All right. So you take each value, multiply by the PMF, and subtract 25, you will arrive at 5. Okay. So we denote this EX to be equal to mu and var X to be equal to sigma squared. Okay. Because we are talking about the population mean denoted by mu and the population variance denoted by sigma squared. Okay. Now you will notice here that EX is 5, and on the previous slide, EX bar is also 5. Okay. Okay, guys, this is not a proof, this is a demonstration, but it's true. Okay. So here, when you in stats, EX bar equals to EX. Okay. And we denote this by mu. In our example is 5. Okay. And variance of X bar, as we've seen here, is 5/2. But now we have seen just now that var X is 5. Okay. So that's var X, that is sigma squared, is 5. And over 2, but this is the sample size, little n. So I have demonstrated that var of X bar is sigma squared divided by n. That is the population variance divided by the sample size. And here EX bar is simply equal to the population mean. All right. So do you have any question here? That's very important. Okay. All right, guys. So the variance of the sample mean is...
Sorry,
yeah.
I just want to know why n is 2.
For our example. What?
Yes.
What's this? How many values do I have in this sample?
2 each.
Yes, so the sample size for each sample is 2. Can you see here? The mean of the samples of size 2. Can you see?
Yes, thank you.
Okay. All right, so it's for this example it's 2, okay? But in fact, what I have demonstrated, it's not a proof. It's not a stats proof. It's a demonstration. I have demonstrated that the variance of the sample mean is the population mean, okay, in red, divided by the sample size. And the expected value of the sample mean is simply the population mean, mu. Is that clear? That's very important, okay? So please make a note there. This is very important. The last, okay, it repeats itself here on slide 7. So please bear this in mind. It's important that you understand this, okay? Although it's given. It's important that you understand that the expected value of the sample is simply mu, and the variance of the sample, E of the sample mean is mu, the population mean, divided by mu sub X. Guys, mute yourself. Mu sub X bar, and the variance of the sample mean is the population variance, divided by the sample size, okay? Denoted by sigma squared sub X bar. And when you take the positive square root of the variance of X bar, we refer to this as the standard error, okay? Guys, please mute yourself. Please mute yourself. Thank you. Okay, so some people call it the standard deviation of X bar, but usually when we talk about the statistic, we talk about the standard error, okay, of that statistic. And again, denoted by sigma sub X bar, because here the statistic is X bar. Okay, so the central limit theorem, okay, basically simply says, okay, on the previous slide, I did not say anything about X. X can be normal or may not be normal. Okay, so, but how do we then find probabilities if we do not know anything about it? So the central limit theorem, abbreviated as CLT, allows us to find probabilities associated with X bar, okay? All right, so what it is then, okay, suppose we have n values, okay, x1 to xn, okay? So this is a sample, okay, random sample of size n, because we have n values, and nothing is said about the distribution of each x, okay? Nothing is said about that. It can be any distribution, any continuous distribution. And but the thing is, with the CLT states that the x bar here, that is taking all these values added up, divided by the total number of values, that is x bar, in turn follows a normal distribution with mean mu and variance sigma squared over n, okay, as we have just seen on slide 7, okay, mu and sigma squared over n for the variance of x bar. So if we have n values and not knowing anything about the distribution of these values, whether they are normal or not, the CLT says that the sample mean x bar in turn follows a normal distribution with mean mu and variance sigma squared over n, okay. So now, since we know that this is normal, we can use the normal tables to find probabilities. Okay, you will remember this, the standardization or transformation from x to z, but it also applies for x bar because x bar is a random variable. So we define z to be the random variable. So in our case here, it's x bar. Subtract the given mean divided by SE, okay? SE or the, when I say, okay guys, one more thing. When I say SE, I imply standard error. I will use that in chapter 5. Okay, so here when you take the positive square root of the variance here, this Z in turn will follow a normal distribution, which means 0, and variance 1, which we have seen previously. We can then use the normal tables. Okay. One more thing on slide 11, this is the theoretical stats. I will not ask you anything about this, okay? But just bear in mind that the magic value is 30, okay? I will come to that again in chapter 5. Okay, 30 is very important, all right? Okay, so I will not ask you anything on this slide, okay? Because it involves theory, okay? So just know 30 is a magic number, okay? Okay, guys, before I do this example, do you have any questions? Yes.
No, not yet. Not yet.
Okay, fine. Okay, so let's have a look at this example where bulbs in a factory follow the lifetime of those bulbs, okay, follow a normal distribution with mean 800 and variance 1600, okay? So in other words here, as you see in purple, X follows normal with mean 800 and variance 1600, okay? And for the purpose of this experiment, we draw a sample of size 10, okay? So here, little n is 10, all right? And here we are required to find these probabilities, okay? So what we know from this setup is that mu is equal to 800 and sigma squared is equal to 1600, okay? So that's the population mean and that's the population variance, okay? By the way, guys, also for chapter 5, instead of saying population, I will say pop, okay? You know that. Okay, so the pop mean is 800, the pop variance is 1600, obviously. The pop STD, sigma, is 40, okay? All right, so let's have a look at these probabilities when drawing a sample of size 10. Okay, guys, so here n is 10. We are required to find the probability that the mean of this sample, okay? Now, when you see problems like this, the mean of this sample, that is, we are looking at x bar, okay? X bar. Now, from slide 7, what will be the distribution of x bar? X bar by the central limit theorem will be normal with mean mu and variance, which is 1600, divided by the sample size, which is 10. Understand that, guys? That's very important, okay, when it comes to this type of problems. Okay, so that is, I have referred to here to slide 7, okay, here, okay. So given mu, we use the same mu. Given the pop variance, we take that pop variance divided by the sample size, okay. And again, x bar from the CLT follows normal, okay? Then we can use the tables. All right, so here, okay, so let's have a look at these probabilities. Okay, so again, we already know now that x bar follows normal with mean 800 and variance 160, okay? Yeah, so here we have the information that we need. We need to transform x bar to z, okay? And guys, bear this in mind that we take it given any continuous random variable, be it x or be it x bar, And when we have either one x or x bar follows normal, we can transform, okay, and call it z. So here we're going to subtract the mean divided by the SE, that is standard error. Okay, so I will leave this to you to do. Okay, so subtract the mean on either side and divide by SE. Okay, again, guys, SE for standard error. So simplify and get a probability of 0.11. Okay, so again, guys, please try this as an exercise. And what's the prob that the mean? Okay, again, guys, when you see this type of problem, the word mean will imply many things. Okay, in this case here, x bar greater than 820. So again, standardize, subtract the mean divided by SE on either side. And guys, be very careful. I explained this before. You have a greater than sign. So to be able to use the table, we need to use this property. Okay, 1 subtract the prob that z is less than. Okay, so it simplifies to about 5% or 6%. Okay, 0.0571. So that's a probability that x bar exceeds 820. Now, very important here. What's the probability that x bar differs from mu? Okay, now can you see the difference here? Eh? Here we talk about the mean of the sample against the population mean. Okay, so bear in mind there is a difference. Okay, in notation. Okay, so that's x bar. So that's the given population mean mu. Okay, so what's the probability that x bar differs from mu by no more than 16 hours? Okay, so here we're looking at the difference, and you've seen this in maths. Okay, difference in this difference here is modulus. Okay, so here mod x bar minus mu is less than 16. Okay, and when you simplify this, when you get rid of the mod sign, x bar minus mu will lie between minus 16 and 16. So we need to find the probability of that. Okay, all right, guys, this is first year maths. Okay, so which means that if you look at the green part here, x bar exceeds mu. Okay, then the difference will be positive and not more than 16. Okay, because x bar minus mu will then be less. Okay, and here as well, x bar, if you look at the purple part here, x bar less than mu. Okay, so in other words, x bar minus mu is less than 0. Okay, but not less than minus 16, and here not more than 16. Okay, so obviously we are looking at this scenario here. Okay, lying in between minus 16 and 16. You guys, again, this is modulus. Okay, it's from first year. All right, so we need to find this prob. Okay, guys, so we need to find the prob that x bar minus mu lies between minus 16 and 16. Okay, you will see here that mu is already there. So there's no need to subtract mu again. So we go directly by dividing by the SE, okay? All across this inequality, okay? All right, so again, the middle part here is Z, and Z here lies between plus minus 1.26. Again, I explained this before. You subtract the smaller probability from the bigger one. Please try this, you will arrive at 0.7924. All right, so basically, I will show you again what I imply by this using a different slide, but here it's just quite easy, okay? Find the probability that Z lies between two values. You subtract the smaller one from the bigger one, okay? And for the last part here, find the prob that the mean of this sample, that is x bar, differs from the actual mean, that is the population mean mu, by more than 16. In fact, this problem here is simply the complement of the previous one. So you take the previous answer, subtract it from 1, okay? Here. But another way of doing this is by saying that the difference must be more than 16. That is, we are looking at x bar greater than mu, so that the difference here is greater than 16. Okay, it's positive. And here, x bar subtract mu is less than 16. Okay, negative. Okay, on either side. Okay, so here we are finding the prob that this difference is greater than 16, added to the prob that this difference is much less than minus 16. Okay. So in other words, we are looking at the complement, okay? That is, this difference lies between minus 16 and 16. But we have already found this probability previously. So instead of doing it this way, it's easier to read that way. And then subtract the prob that you find from 1 to arrive at the answer. Okay, what I mean by this is that here, I'm going to use a slide that we have seen previously, okay? So AB minus 16, 16, okay, you find this prob. for the part C, and for the part D, we are looking at the white part, okay? So obviously subtract this probability from 1 to get the probability of the white part, or the area of the white part, okay? So that's all what it means, okay? So we just had a look at this situation where we have this scenario, okay? So, but Z was Z, all right? Z between two values, and obviously for the part D, it is a complement of this probability. So subtract this prob from 1. 5.3, 5.4, okay? So this is at the heart of statistics, okay? It's very, very important. And sometimes it is referred to as inferential statistics instead of statistical inference, but it's the same thing. Now remember, at the beginning of the semester, I said that we have a population, and from that population, we draw a sample. And from that sample, we do some calculations to infer on the population, okay? So for example, if we have 10 million kids in this country, we want to find the mean height. So let's say we draw at 5,000 kids from those 10 million, measure the heights and find the average, okay, the sample average. So that average, the sample average, will give you an idea of the population mean, okay? So X bar will give you an idea of mu. Okay, so I have a few examples here, you can read by yourselves. Okay, so statistical inference consists of two parts, hypothesis testing and estimation, and wherein under estimation we have point estimate and interval estimate. I will come to that later. Okay, so in this course, we will focus only on mu, the parameter mu, and by using the statistic X bar to infer on mu, okay? So bear in mind, we will focus on mu, but at a later stage, we will also use S squared, okay, under different conditions. But our focus will be on the mean, the pop mean mu, okay? So a sample estimate of a parameter is referred to as a statistic. That is, X bar here is referred to as a statistic. And again, we have different parameters depending on the situation. So we can have proportion, mean, and variance. As I said, we'll focus only on mu. All right, so we need to know some terms, okay, some terminologies. Okay, so again, as I said, a point estimate is simply a single value, as the name suggests, it's a point. So it's a single value on the real line, whereas an interval estimate obviously is an interval. And an interval contains a lower value and an upper value. And we associate a confidence percentage with that interval. And we say that the interval, we are certain to some value that the interval contains the parameter. Okay, we will have a look at this now. Okay, let's have a look at an example where we want to understand the mean time it takes to serve customers at a supermarket. And here, let's say we have 100 customers, okay? So in our sample, we have 100. Obviously, in a day, in a big place, there are many more. There are more than 100 customers. But we can afford to only measure the time, the service time for 100 customers. And we arrive at an average of X bar, which is equal to 2.283 minutes. So this is just a single value. It is referred to as a point estimate for mu, okay? So again, guys, if you have another 100 customers, this X bar here will change and so on. And that is why it's better to work with an interval rather than a point estimate. So for this same example, we have an interval here. This is referred to as an interval estimate running from 1.6 to 4.0, okay, to one decimal place. And as I said, we place a percentage to that interval. So we say that we are 95% confident that mu will be in this interval, okay? That is, mu will be in this interval with a 95% confidence. Okay, so I will show you how to find the confidence interval or the interval estimates as we proceed. And again, guys, it's better to work with an interval estimate rather than a point estimate, because if you have another 100 people, X bar will change, okay? So let's have a look at some more terms, okay? So again, guys, as I said, we'll focus only on mu in this course, okay? So here, theta, the generic theta, will represent mu, okay? And again, we have other situations where we can infer on sigma squared or p, but again, this is not our concern. Sigma squared and p are not our concern, it's only mu, okay? So obviously, guys, an interval contains two values, a lower value and an upper value, and these are referred to as lower confidence limit and upper confidence limit respectively. And these two values make up the confidence interval. And as I said earlier on, we talk about a confidence percentage, okay? So how confident are we that this interval contains the parameter theta? And this is given by 1 minus alpha by 100, okay? Or 100 into 1 minus alpha. And this coefficient here, 1 minus alpha, is referred to as the confidence coefficient. Okay, sorry. Yeah, the 1 minus alpha is referred to as the confidence coefficient. And it is simply a probability. Of course, multiplied by 100, it gives you a percentage. Okay, so for the same example that we've seen just now at the supermarket, the time taken. Okay, so in that example, L and U, okay, are the different values here, 1.6 to 4.0. And we say we are 95% sure that mu will run from the lower value to the upper value, okay, obviously. And when we divide by 100, we obtain the confidence coefficient. Again, you will see it is a value between 0 and 1, and here it is simply 0.95. That's a probability. And again, I will come to the alpha at a later stage, but just know that we also need to find alpha, okay? And here, theta represents mu. Okay, so there are many conditions, okay? The first one is, guys, for confidence interval, I will say CI, okay? Confidence interval. So for the first part is the CI for mu, okay, for the pop mean mu, when the pop variance sigma squared is known, okay? So that's the first condition. When sigma squared is known, how do we construct a CI for mu? Okay, for the same example, we have x bar, and again, x bar is simply one value. It is a point on the real number line, okay? So 2.283 obtained from one random sample of 100 customers. Okay, so we will also talk, okay, the real value for mu may be less than x bar or greater than x bar, okay? Let's say we have a CI running from 1.283 to 3.283, okay? So you would observe here that the difference between 1.283 and 2.283 is 1, and from 2.283 to 3.283 is also 1, okay? And in statistics, we refer to this value, to the difference between x bar and the lower value, and x bar and the upper value by E, okay? And E is referred to as error, okay? And bear in mind that mu can be 1.283 itself, or 3.283. That's why we say we have a certain percentage, in our case 95% confident that mu, the true value mu, will run maybe anywhere between 1.283 and 3.283, okay? And the x bar here is simply an estimate on the real number line. Okay, where obviously mu can be less than 2.283 or greater than that. Okay, so in our case, as I said again, okay guys, there's a typo here at the bottom here. If mu is equal to 2.283, it should be 3.283, okay? The distance from the lower distance is 1, okay? 1.283 to 2.283, and the upper distance as well is 1. So 1.283 to 3.283 minus plus 1, okay? So you will get, as I said, for this example, this value 1 is simply the distance E, which is equal to 1, okay? So another way of writing the CI is by stating this, okay? X bar plus or minus E, okay? Where E again is the error term below and above X bar, okay? But how do we find E? And how certain are we that the interval contains the parameter theta, okay? So for this purpose, we will have a look at the theory. But for your purpose, you need not know the theory because the formula will be given, okay? But it's always good to understand how we arrive at the formula. So let's have a look at this, okay, when sigma squared is known. All right, guys, that's why I say chapter 4 is very important. We make use of the standard normal distribution. Standard, that is, we're going to be using the random variable Z, okay, big Z. All right, so we've seen earlier on 1 minus alpha, okay? 1 minus alpha here will be the probability in the white region. And of course, total probability is 1, so that the missing probability is alpha, okay? But since by symmetry, the area in the red regions will be alpha over 2 on either side, okay? So if you add all the terms, you will get 1, that is alpha over 2 plus alpha over 2, that's alpha, minus alpha is 0, plus 1 is 1, so that the total area is 1, okay? And here, notation is very important, okay? The Z values that you see here are very important. And as I said from chapter 4, we always measure from a small value to the given Z value. So here for notation, because the area to the left here in this red region is alpha over 2. So the Z value is written as Z sub alpha over 2. And the line of symmetry obviously is 0. And the value here from a small value to the given Z value, okay, the on the right hand side here. Okay, so the total area from a small value to this given Z value will be 1 minus alpha plus alpha over 2, which is 1 minus alpha over 2, okay, because minus alpha plus alpha over 2 is minus alpha over 2. So this Z value is written as Z sub 1 minus alpha over 2. Okay, so by symmetry now, this Z here, this Z sub alpha over 2 can be written as minus Z sub 1 minus alpha over 2, that is by symmetry about the line 0, okay? So we have plus minus Z sub 1 minus alpha over 2. All right, as I said, these two values are very important. Okay, so again, the probability in between these two values is 1 minus alpha. So any random variable Z will be between these two values with probability 1 minus alpha, okay? Now, why we are using Z? Because from chapter 4, you will remember that Z is given by this expression, bottom right, okay? X bar minus mu divided by SE, where SE is sigma over root n, okay? So that when you substitute for Z in here, we have the middle term between those two Z values, minus plus Z sub 1 minus alpha over 2, and this probability is 1 minus alpha. Okay, so from here we can solve for mu, okay? I will not do this part for you. This is from high school, okay? Cross multiply, add, etc. Okay, so you will arrive at the last line here, where mu lies between these two values with probability 1 minus alpha. And so here the only difference is the signs, okay? So on the left-hand side, obviously it's minus, and on the right is plus, okay? So mu lies between these two values with probability 1 minus alpha, that is the confidence coefficient. Okay, so this again can be rewritten as such here, okay? 100 into 1 minus alpha percent Ci for mu when, okay, this is very important, this is the condition. The condition is that the pop variance, sigma squared is known, and we obtain the following limits, okay? Confidence interval. Again, so the only difference is the plus minus from the previous here, minus, plus, and the remaining terms are the same, okay? And this will be provided on the formula sheet, okay? As you see here. And earlier on, we had a look at X bar plus minus E. Obviously here, E is equal to the Z value by SE, okay? And the Z value for our purpose is referred to as the Z multiplier, okay? So X bar plus minus Z multiplier by SE, okay? So that's our Ci for mu when sigma squared is known. At a later stage, we will have a look at the Ci when sigma squared is unknown, the second case. All right, so let's have a look at the example. I trust you have read this, okay? So in this example, sigma is known, okay? It is said here to be 5. Obviously, variance will be 25, and n is equal to 30, okay? A random sample of 30 cans is selected at random, okay? So here it's going to be 30. And when you measure the content, you have X bar. So that's the mean content is X bar, because we use X bar here because we're looking at 30, a sample size of 30. So giving 498.95. Now this is mu, okay, 500. All the cans, when you go in a shop, you look at the can, you might see 500, but is it really 500, okay? So we want to test that. What's the value of mu for all bottles? At the bottom here, all bottles. That is the population mean. Is it really 500? I will come to that later, but here I'm just demonstrating the Ci, okay, the confidence interval. Okay, so the first part is to find the 95% Ci. We have all the info. We need to find the Z multiplier, okay? It's very important. So the first step is to find the term 1 minus alpha over 2. Okay, here we are looking at 95% confidence interval, confidence percentage. Okay, so as I said previously, this is given by 1 minus alpha by 100%. So solve for alpha, and then divide by 2, subtract the new value from 1, okay? So here you will arrive at 0.975, and we need to find this is Z sub here, Z sub 0.975. And again, guys, please find the value by yourselves from the normal tables, okay? And as an exercise, as a practice. Okay, so you will see that it is 1.96. And we have all the information now to plug into the formula and solve, okay? And simplify. So here the 95% Ci for mu when sigma squared is known, okay, obviously, see sigma squared here is 25, but we use sigma. according to the formula, and then simplify to the last line here, okay? L and U, giving the two values for L and U respectively. Okay, so this is for 95% CI, and the second part stays for 95% CI, okay? Again, the same procedure. Okay, this is the way I do it, okay? Okay, so here we need to solve for alpha, and then alpha over 2, subtract the new value from 1 to arrive at 0.995, and then find Z sub 0.995, and you look at the table, it will be 2.576. Use this value together with the previous information, yeah? Substitute into the formula, and then simplify to get the two values for L and U respectively, okay? Okay, one hint here, is that the larger or the higher the percentage, the confidence percentage, the wider the CI, okay? If you look at the difference here, I think it's about 4.7, so it will be larger or wider than this one, okay? So again, the higher the confidence percentage, the wider the CI. Okay, so again, guys, you have received an email from me yesterday. Okay, I'll ask you to do this by yourself. Again, it's very easy. I'll give you the hint, okay? The hint is from here, okay? E is Z by SE, when sigma squared is known. So from here, so E equals to the product of these two terms, okay? Obviously, in a problem, E will be given. So your job here is to find N, okay? So there's some various hints, which you can read by yourselves, okay? And from here, slide 26, okay, solve for N, okay? So N is given by this term, all right. Okay, guys, so this will be provided on the formula sheet, and the trick here is that given a certain E, for any case, in any case, we have to always round up to find N, okay? So that the error term is not exceeded, obviously. Okay, so sometimes the error will be provided straightforward, and sometimes it may not be provided straightforward, okay? So you have to figure it out from a problem. Okay, so again, guys, we always round up for N, okay? For example, here it's 47 point something. So we round up so that the maximum error is not exceeded. Using 47 and 48, and again, the maximum value must not be exceeded. That's why we always round up, okay? And guys, that's the way I do it. And you see the purple part, okay? For me, as a guide for myself, okay? So I would suggest that you do it the same way. Okay, for the slide on 28, same idea, okay? So the catch here is to get the correct value for Z, okay? Obviously. Okay, guys, so please do these slides on how to find the sample size, okay? It's quite neat here. The explanations are quite neat. It's fine.